We're going to look at the idea of a limit. So we kind of have two main parts to look at. We're going to look at generally starting off what is a limit. So kind of summarizing that idea of what does a limit mean. We'll look at it a little bit more in functions as well when we're talking about continuity and things like that within a function. But here we're just kind of setting up the general idea of what a limit is. And I suppose from its kind of simplest definition, a limit is the value that the function approaches as x approaches a particular value, or as the input approaches a particular value. And that's kind of what I just have in the first line here. So the limit of the value is the value that the function approaches as the input approaches a particular value. So if we're looking at a graph, or if we're looking at a particular function on a graph, we might want to know what is the limit, what value is this function going towards as x gets closer to 2, for example. And for many functions, that will just be the value of the function when x is 2. So that's what I said in the second part here. So in limit notation, if the limit as x goes to a is equal to p, then that means that f of a is equal to p. Okay, it's fairly straightforward, and that's our general case for a limit. If it's just standard, if we can sub it in, if it works out properly, then that is the case. And this is also a sign for us that a function is continuous. Okay, so this is actually a sign of continuity. That's not right. I can't spell. Continuity. We'll just go with that. So continuity, that's a sign of continuity for a function. If the limit of the function as x goes to a particular value is the same as f of that particular value, then the function is said to be continuous. So generally, standard case, if you're given the limit as x goes to something of a function, you just sub in that value for x, or for the input. I suppose looking then at this second part here, this is more where we get into kind of more complicated limits. So it's called what we might call the indeterminate case, or where a function's undetermined. And where a function's undetermined or undefined is generally when we end up with something like this here, where we have maybe 0 divided by 0, or anything divided by 0, because we can't divide by 0. That's kind of, it's not defined in terms of maths to divide something into 0 parts. So in those cases, we have to factorize before applying the limit. So in these cases, what we'll do is we'll start off, we might sub in, a lot of the time we'll be able to see from the examples that it's an indeterminate case, but we can sub in, we can get this kind of undefined value, so this division by 0 generally, and then if we encounter that, we know that we then have to maybe factorize the numerator or one part of the fraction, and we can reduce the fraction down further and then apply the limit to the function. And the key thing to note here is that with a function like this, where it's an indeterminate case, there is no value of f of a, but there is a limit. So the function gets closer and closer to this particular value, but the actual value of f of a doesn't exist because it's not continuous at that point. So that kind of calls back to what we were saying here. It's only continuous if the limit and the value of the function are the same for this particular input. In this indeterminate case, we won't have a value of the function, but we do have a limit. So looking at this first example then, it's the limit as x goes to 1, and we can see this notation here, so we generally write limit with the x goes to underneath it, and then we have our function x squared minus 3x plus 2 over x minus 1. Now I can see from looking at this already that because we have x minus 1 on the bottom, and we're going to be evaluating when x is equal to 1, that bottom part, the denominator, is going to go to 0. But we'll do what we would normally do, which is we will try it out first. So let's just sub in our value. So the limit as x goes to 1, so let's evaluate that limit. So evaluate. So we're just going to sub in 1 anywhere that we see x, and we're going to evaluate the limit here over 1 minus 1. So that gives me 1 minus 3 plus 2 all over 0, which of course is just going to end up with 0 over 0, which is my indeterminate case. So that now means, or tells me, that I'm going to have to factorize. And looking at this question, the only thing that I could factorize would be the numerator there, because that's a quadratic. And if I simplify or factorize this quadratic, I get x minus 2 and x minus 1. So if we simplify our question here now, so we're looking for the limit as x goes to 1 of x minus 2 over x minus 1 divided by x minus 1. And because we have the same term, the same expression on the top and the bottom of my fraction there, I can reduce that down to the limit as x goes to 1 of x minus 2. And then evaluating that 1 minus 2, I get a value of minus 1. So the limit of this function as x goes to 1 is minus 1, but the actual value, the function has no actual value at x minus 1. It has a limit, but it has no actual value. So let's look at one or two of these questions. The first question here, again, just practicing our limits, we're evaluating the following limits. So let's start by just evaluating as normal. We're just going to sub in the value for x. So we have 2 times 3 squared minus or plus 5 times 3 minus 7 over 3 plus 3. So 2 times 9 plus 15 minus 7 all over 6. Again, we're simplifying down, so 18 plus 15 minus 7 all over 6, and that's going to give me 26 over 6, which will reduce down to 13 over 3 there. So we have a nice kind of straightforward, just evaluate the limit. We didn't end up with any indeterminate case there, so we don't have to factorize. We only factorize if we have that indeterminate case. Looking at the next example, x squared minus 5x minus 14 over x minus 7 evaluated at x is equal to, or as x goes to 7. Again, we can sub in, but we should be able to see, similar to the first example we did there, that as we sub in for 7 here, we're going to end up with our indeterminate case. So 49 minus 35 minus 14 all over 0, and on the top I get 0 as well. So I get 0 over 0, which is my indeterminate case. So I need to factorize. I'm going to factorize the top part here, minus 5x minus 14. If I factorize that, that's going to go to x minus 7 and x plus 2. So to simplify my question now, it's the limit as x goes to 7 of x minus 7, x plus 2 all over x minus 7, which is just going to give me the limit as x goes to 7 of x plus 2, which is 7 plus 2, which is of course 9. So for that case there, we have our indeterminate case, so we know that we have to factorize before applying our limit. But it's always good practice to try and apply your limit first and then result in that indeterminate case and then kind of sub in. But obviously for ones like this where you can see immediately that it's going to result in a division by 0, then you could just jump straight to applying your factorization there. So looking at this example, then the same thing we can kind of see already is going to happen. 2 cubed minus 8 over 2 minus 2 is going to give me 8 minus 8 over 2 minus 2, which is of course 0 over 0. So again, an indeterminate case. So we need to factorize. The top part here can be factorized. It's a difference of 2 cubes, so I can rewrite it as x cubed minus 2 cubed, and then writing it in my difference of 2 cubes format, x minus 2, x squared plus 2x plus 4. Okay, x squared plus 2x plus 4. Reducing this down then, so we're getting the limit as x goes to 2 of x minus 2, x squared plus 2x plus 4 all over x minus 2. So it reduces down to the limit as x goes to 2 of x squared plus 2x plus 4. I can evaluate that limit, 2 squared plus 2 times 2 plus 4, which is 4 plus 4 plus 4, which is of course 12. So same thing again, you can see how it's important here that we know our factorization rules also, not just kind of applying the limits, so everything kind of ends up being related somehow. We've one other type of limit to look at here, and it's the limit as x goes to infinity. So when we talk about x going to infinity, we're just talking about if I increase x as far as I possibly can. And we can actually look at that going in both directions, so positive infinity or negatively towards infinity, and kind of going either direction on your number line as far as possible. And with this, we're going to be making use of some fractions here. And this is what I'm getting at with this example. So if we look at 1 over x as the value of x increases, so that's obviously the denominator, as the denominator increases, the overall value of the fraction itself is actually getting smaller. And we can see that by looking at the decimals. It makes it a little bit clearer for us. So we have 1, we have 0 0.1, 0 0.01, and we can see the decimals getting smaller and smaller and smaller. And what we say is that as that function increases, it tends towards 0. It's getting smaller and smaller and smaller until it's nearly infinitesimally small. Okay, it's really, really small. And then we essentially say that it's tending towards 0, that the limit is going towards 0. And we're going to be making use of that in these questions. So if we have 1 over x and we get the limit as x goes to infinity, that's going to be equal to 0 because it's tending towards 0. The same thing happens if we have a case here where it's something over x. So say 2 over x, the same thing is going to happen. It's going to tend towards 0. If we have a case where maybe it's x squared on the bottom instead of just x, that again is going to tend towards 0, and in fact probably more quickly is going to tend towards 0. And similarly, if we have k over x to the power of n. So in general, when we're trying to find the limit to infinity, because we can't sub in for infinity, because infinity doesn't have a value in that sense that we can sub in for, in general, what we do is we try and make use of this rule. So we're making use of this idea that if I have a fraction and I use the limit towards infinity, that that's going to be 0. So we try and create these fractions within our questions. So in these cases here, we divide the numerator and the denominator by the highest power of the variable. So the highest power of the variable. What we're trying to do is we're trying to have terms that have no variable in them, and then have terms that have got variables in them. So we're trying to, in some cases, have no variables so that we have a limit result at the end, but then in other cases that do have a variable, we want only to have variables on the bottom of the fraction. That's kind of the idea that we're going for, and the best way to achieve that is divide by the highest power of the variable. And in doing that, we're kind of ensuring that if there are variables, they're only going to be on the bottom of a fraction. So when we evaluate our limits, then we end up having no variables left. So looking, say, at this first example here, I can see that the highest power of the variable is the x squared here. So I'm going to divide the top and the bottom of my fraction by x squared. So I'm getting the limit as x goes to infinity of 8 over x squared minus 4, because 4x squared divided by x squared just gives me minus 4. 9x squared divided by x squared just gives me 9. The 5x divided by x squared is going to end up just being 5 over x. If I evaluate the limit now, because this is a fraction and this is a fraction over x, they're both going to go to 0. So evaluated by limit, that goes to 0. The minus 4 stays the same, 9, and this also goes to 0. So I get minus 4 over 9. So as this function, as the inputs get bigger and bigger and bigger, this function tends towards minus 4 over 9. It has a limit of minus 4 over 9. Looking at this example here, the limit as x goes to infinity of this question, we can see again that the highest power of the variable is this x to the power of 5 here, x to the power of 5. So we're going to be dividing the numerator and the denominator by x to the power of 5. So it becomes the limit as x goes to infinity of, let me see now, x cubed divided by x to the power of 5 gives me 1 over x squared minus 2 over x to the power of 4 plus 11 over x to the power of 5, 3 over x to the power of 5 minus 6. Evaluating my limit here, now all of these terms are going to go towards 0 because they are fractions with an x on the bottom. As that denominator gets bigger and bigger and bigger, the overall fraction is going to go towards 0. And we're going to end up with an interesting expression here. We have 0 over minus 6, and if we're unsure whether that can happen, let's just type it into my fraction. Can I have 0 over 6? I can. That just results as 0. If I split 0 into 6 parts, I end up with 0. So that has got a limit. It has a limit of 0. An important thing to note there, I suppose, just a kind of aside, we can have 0 over something, but we can't have something over 0. That's kind of comes back to what we were saying earlier. 0 over 6 is 0, but 6 over 0 is undefined. Okay, they're saying complex infinity, it's undefined. It's not that we don't have a defined value for that. So we can have this, but we cannot have this. Okay, let's just look. I think we have two exam questions here. So one from the most recent year, 2023. This exam question makes use of a particular rule with our limits that we kind of haven't touched on yet. So it's a good example, it's a good chance to show it. And that is that if I have an expression like this one here, and I'm taking the limit of the overall expression, that is the same as me rewriting this question and taking the limit of each part of this expression. So if I take the limit as n goes to infinity of this part, plus the limit as n goes to infinity of this part, plus the limit as n goes to infinity of the last part. So we're taking the limit of each of those individual parts of my expression, my terms of my expression. So if I have a function or an expression here that's a sum of two functions or three functions as we have, that's the same as me taking the limit of each of those individually. Okay, taking the limit of each individual one. So we're taking this part over here, and we're taking this part as this middle limit, and we're taking the last part then as my last limit here. Okay, so taking each of them individually. So let's just tackle each of those the same way we did in the first ones. For limits to infinity, we divide the top and the bottom of my fraction by the highest power of the variable. In this case, that's just going to be n. So n divided by n is just 1. Working 1 over 1 plus 1 over n. Okay, so dividing top and bottom by n there. We're doing the same thing now in the second part. Again, the highest power of the variable is just n, so 100 over n over 1. For the last expression here, we have something a little bit different. So the limit as n goes to infinity of 1 over 3 to the power of n. So for this one, we're not going to be dividing by any particular powers or anything like that. But we have a particular result that we can make use of here. And what we need to do is we need to think about what this means. What do these powers mean? Well, if it was 1 over 3 to the power of 2, that would be 1 over 9. If it was 1 over 3 to the power of 3, that would be 1 over 27. If we do 1 over 3 to the power of 4, that's going to give me 1 over 81. And we can see that similar to what we had earlier, as that power increases, so goes 2, 3, 4, and so on and so forth, the denominator of my fraction is getting bigger and bigger, which means that overall my fraction is getting smaller. So the fraction is getting smaller as n increases. And what we can say here is that the limit as n goes to infinity of any kind of fraction here, and it is important that it's a fraction. It is important that it's a fraction. So if we say 1 over k, it doesn't matter, to the power of n, that is going to go towards 0 because the fraction itself is just being multiplied by itself over and over and over again. And because of that, it means that the fraction itself is actually getting smaller. And that comes back to the same example we had earlier. So as the fraction gets smaller and smaller and smaller, the limit then will go towards 0. Okay, so we can straight away evaluate that limit, but what we'll do is we'll leave it for a second. We'll evaluate all the limits together. But just so that we have that idea that as I evaluate that limit, we don't need to do any changing, but we know that as that n would get bigger and bigger, my fraction itself would get smaller and would go towards 0. So evaluating each of my limits here, so the first limit, I have 1 on the top, I have 1 here, and this 1 over n, this 1 over n here will go towards 0. Evaluating my second limit, I have something similar happening here, and this part here will go towards 0, the 100 over n. And lastly, we've said that this whole last expression will completely go towards 0. Okay, the whole expression goes towards 0 because the fraction would just keep getting bigger and bigger. The fraction itself would get smaller as the denominator gets bigger. So that's going to give me 1 plus 1 plus 0, which is of course 2. So two good things for us to note there. The first one being that we can separate out the terms or the parts of my expression there, or the different functions that I have. So essentially saying as if this was f of x, g of x, and h of x, if you like, that we can split those out and take limit of f of x, limit of g of x, limit of h of x. And the second part then being this idea of powers of the fractions. So we have a fraction to a power, and as that power gets bigger, the fraction itself will get smaller and tend towards 0 in the same way as we had before. It's kind of just a different rewriting of one that we've already seen. The next question we're going to look at is from 30 years before, 1993. And again, limit as x goes to infinity. Limit as x goes to infinity. So we're applying the same way. What we're going to do is we're going to divide the top and the bottom of my fraction by x squared, the highest power of the variable. So we can see it here. So let's evaluate that. So the limit as x goes to infinity of 2 plus 3 over x plus 4 over x squared. 1 plus, or sorry, minus 2 over x minus 3 over x squared. So now that we've evaluated that, we can see, similar to the last questions, and this is always why we divide by the variable, every time a variable appears now, it is on the bottom of the fraction, which means that all of those fractions will tend towards 0. So we end up having just 2 over 1, which of course is just 2. Okay, so each of those yellow parts there that I've highlighted, they will all tend towards 0 if I evaluate that limit, and I just end up with a result of 2. So actually the same as the last question. So I suppose that's the only two exam questions we have there on those limits to infinity and on the limits generally. So it's maybe not the most common. It comes up in maybe some other parts. We'll see it in differentiating by first principles. We kind of make use of our limits there as well. But just generally to note this idea of the two different types we have. So we have the limits to a constant, where we can maybe sometimes have that indeterminate case, and we then have the limits to infinity, where we have to divide by the variable, and always trying to get any variables we have on the bottom of a fraction so that we can evaluate that limit and say that it tends towards 0. So those are kind of the two main things for you to watch out with in terms of these limit questions.